Welcome to our final lecture on computer engineering. For this day, we'll cover sequential logic. So, what is sequential logic and why do we need it? Well, to understand that, we need to know a little bit about something called a state machine. A state machine is the way that almost all digital electronics work. You can't just have one logic equation to govern very complicated things like microprocessors. You need to have states. These states define how the logic equation will behave based on previous inputs. Let's think of an example of a state machine. A counter is a very good example. A counter has to know what number it has counted past and/or is on currently. So, if we can't hold within our circuit the internal count, our counter won't be very helpful. So, how do we do this? Well, previously we looked at combinational logic and K-maps to cover how to determine the combinational logic equations for what our circuit was. For a sequential logic, we use state diagrams. State diagrams show us what state our current circuit is in. For an example, you can see we have 4 states here represented by circles. And we have an arrow going to each state. This diagram says that from state 0, 0, we can go to state 0, 1. From 0, 1, we can go to 1, 0. And 1, 0, we can go to 1, 1. And from 1, 1, we can go back to 0, 0. We could change this if we drew another line going this way. This means that now we can go from 0, 0 to 0, 1. Or we can go from 0, 1 to 1, 0, or 1, 0, 1 to 0, 0. We could also skip ahead normally, or maybe we can skip to this state. With these diagrams, it becomes a lot easier to design a circuit that is sequential logic. So, how do we use this internal memory? Because clearly we have to know what state we're in. Well, that's where perhaps one of the most useful basic circuits comes in to play. This is called a D flip-flop. D flip-flops and D latches are one of the most important ways that we can hold memory or hold values within a circuit. I won't go into exactly how they're made because they're a little bit complicated for their logic diagram. But suffice to say that instead of just having an input, we now have something called a clock input. A clock signal is merely an oscillating pulse between 1 and 0 that happens at a regular frequency, such as 10 Hertz, 100 Hertz, or 100 megahertz, or 2 or 3 gigahertz. You might recognize these terms from things such as your phone or computer processor. Computer processors usually run around 2 gigahertz. This means that their clock signal is right around 2 billion pulses per second. That's very fast, and that means that their state machines are able to work at that speed. So, how does this D flip-flop work? Well, this data input takes in a value every positive clock edge. There's a positive and a negative clock edge for each clock signal. This is the positive edge because it's rising, and this is called the negative edge because it's falling. So, on the positive edge of a clock signal, the D value will be taken in and be sent to either the Q, and then the inverse will be sent to the Q naught output. D flip-flops can also have a synchronous or an asynchronous reset. This reset signal up here, if asserted or set to 1, for our circuit at least, will remove the output from Q and Q naught, regardless of what the value of D is. If it's asynchronous, this means that at any time we can set this signal, regardless of the clock signal, and Q will go back to 0. If it's synchronous, it means that it will only change back to 0 on another clock signal. So, now that I've explained a little bit about this D flip-flop, let's look at our final slide for this lecture. This is another example of what I was saying. This is what you'd call a waveform diagram. The waveform diagram shows the function of the D flip-flop. I'm not showing the Q naught signal because it's merely the inverse of the Q signal. But here's D, here's Q, and here's clock. So, if we notice, we'll assume everything starts at 0. So we have our clock pulses, D is at 0, and Q is at 0. On the first positive clock edge, D is at 0, so Q stays at 0. On the next falling edge, D is still at 0. Now, my diagram is not very good, but let's assume that these are lined up. So, on this positive clock edge, we look at the value of D and say it's a 1, so Q is now a 1. This falling edge, we don't do anything. Even if D had fallen to 0, we don't mind. This positive edge, Q, goes to 0 because D is now 0. You'll notice that D can change very quickly, but as long as it's low or stable, when the clock signal goes high, that value will be, quote, clocked in to our Q. So, if we go through here, we can see, again, rising edge, and we have a 1, so we have a 1 now. Here, I've shown an example of what can happen if Q changes quickly, if D changes quickly, without a rising clock edge. Here, notice that D goes from 1 to 0 and back to 1, all in the time that the clock signal is at 0. And as a result, there's no change on the Q signal. So, this has been an introduction to D flip-flops. D flip-flops are a relatively advanced concept, so we're not going to cover any more information about them. However, I encourage you to look up more information online or to pursue a computer engineering degree at your favorite college if this is interesting to you.